So before we move on, I would like to briefly review the normal distribution. So the normal distribution, you must have studied the normal distribution in statistics course, but I want to review this one more time here. So what does it remind you when you heard about normal distribution? What do you still remember? At least I think you may remember the curve of normal distribution. How does it look like? It is a bell-shaped curve. So if there is any output or value here, x, the value of x is not just one fixed value, but it changes over time. But if you consider the distribution of this x, it is a kind of symmetric distribution. So at the center, what do you have? The average value of this x. And the Greek letter we use to represent average is mu. And given this average, it is nicely distributed. But if it is distributed, what this means is it's not just one value, but there could be many different values can be observed as a value of this x, right? So why you have those different values? Because the distribution of this x has some variance or standard deviation. So to describe the difference, we use a term called standard deviation. If you remember, we use in general the Greek term sigma. Or if you think about the squared value of this sigma, it is called variance. So given this average and the standard deviation mu, we can think about the distribution of a variable x. And since x is varying over time, strictly speaking, we say this is random variable. So we say that a random variable x has a distribution. So we use the sign tilde, the wave sign. So x follows what distribution? Normal distribution. So we use n to describe the normal distribution. And if you want to show normal distribution, at least you need two parameters. The first one is average. Second one is standard deviation or variance. So when you describe normal distribution, we use two parameters inside this parenthesis with a comma. The first parameter you show is average, so mu. Second parameter you show is not sigma, but actually sigma squared. So variance is shown as a part of this normal distributions. Another interesting characteristics of normal distribution is given certain range, we can get the probability by measuring the area under this curve. So what this means, here at the center we have average, right? So standard deviation of this normal distribution is given. Then, for example, let's say there is a value of x, and this value is 1 sigma of difference from the average value. So the distance from mu to this new point is, let's say, sigma. And on the left side, we can also think about same distance. So with the same distance sigma is from this mu, then the point here is mu minus sigma, right? So in that case, what is the probability when x has the value between these two range? In other words, we can say that the probability of x between mu minus sigma and mu plus sigma, it is given as 68% here. But what this 68% means? 68% actually means the area of this curve. It is 0.68 or it is 68%. Okay? So using this bell-shaped curve of normal distribution, what we can measure? We can measure the probability when x has a certain value inside the range. But some students actually misunderstood the probability of normal distribution when they look at this bell-shaped curve. What I mean is, if, for example, just as an example, if I ask what is the probability when x is exactly mu plus sigma? Can you get this probability when x is exactly one specific value mu plus sigma? What this means? This means when x is exactly this 1 point, then actually the area when this specific value is given for this x, can you measure it? No. For example, let's say very, very small difference is given here. And if you want to know this probability when the value of x is between this value and that value, you may find this tiny area as a probability. But as you can see in this curve, if you choose just one specific value, actually the probability of getting that one specific value is what? Almost zero. Because the curve, the area under this curve is just one line and it's just zero. So when you use this standard normal distribution table, make sure we are not looking for the probability of event when x is one specific value. Instead, what we are looking for in general, we are looking for the probability when x is between certain range. When x is in certain range, then we can get the area here, and this area represents the probability. Okay, now similarly, we can further increase the area. For example, let's say this is mu plus 2 sigma, and then this is mu minus 2 sigma. Then what is the probability when x is mu minus 2 sigma and mu plus 2 sigma? So in this range. So now the area is what? Getting bigger, right? So definitely the probability is bigger than previous one. And in this case, it is almost 95 or it is 95%. So we have 95%. Okay, the last example. So how about mu plus 3 sigma? And here is mu minus 3 sigma. Then now we want to think about probability when x is in a wider range between mu minus 3 sigma and mu plus 3 sigma. Then again, what is the probability? The area in this specific range. So in that case, this is actually 9974, almost 99.7%. So 99.74%. You don't have to memorize it, but this, three values are kind of a special case. So many times when you solve a lot of problems again and again, you will just automatically remember this value. Okay, so if we solve some sample problems, you may better understand. So to make it a little bit easier, although it's not directly related with product quality, I wanna give you some typical examples used in statistics textbook. Okay, so in this example, we have the height of a young woman, and this height approximately follow normal distribution with averages. So this average is mu, and the standard deviation is 2.5. So from here, what we can read, standard deviation sigma is 2.5, but the variance is 2.5 squared value. Okay, so given mu and the sigma, we have one unique normal distribution, and it is given here. So the average woman's height is 64.5 and standard deviation is 2.5 inches. Okay, the number one, the question is percent of young women between 62 and 67. So in this picture on the left side, this X value is woman's height. And we want to know the probability when this X is between 62 and 67. So graphically, where you can find it, here's a 62 and here's a 67, and we are looking for this area. Okay, so when you look at this graph, you can actually easily guess, but what you need to find, this number 62, lower range, and upper range 67, how it is related with mu and sigma, because in the previous slide I showed you three special cases, mu minus, mu minus sigma, 2 sigma, 3 sigma. So we have to check whether we can represent this 62 with mu and sigma. So what is mu? 64.5, and what is sigma? 2.5. So let's check it. 62, that is compared to the average 64.5, it is less. So less than 64.5, but we want to know how much less than 64.5, particularly relevant to this sigma, so 2.5. So I don't know how many sigmas is the difference between that specific value 62 and this average. So the difference you will easily find, the number you have here is, yes, it's different by just 1 sigma, right? So you can find that this 62 is particularly, it is mu minus 1 sigma. So mu minus 1 sigma is matched with this 62. Similarly, we can find the matching value for 67 as well. 67 is 64.5 plus 2.5, then how many 2.5s? 1 sigma, right? Then you will get 67. So in other words, this is mu plus 1 sigma value. So this value is particularly mu plus 1 sigma. So we know that in the previous result as a property, when the area is between mu minus sigma and the mu plus sigma, what was the probability? 68%, right? So again, in this picture, it is also given there is a 68% probability when x is between 62 and 67. So this is a 68%. So second question, percent of young women lower than 62 or taller than 67. So what we want to know, probability when x is lower than, so 62, but taller than 67. So we need to consider another probability. So sum of two probability when x is taller than, so greater than 67. That's what we want to know. So graphically, what does this mean? Here is the boundary. It's actually the same boundary. And the 67 is also the same boundary we used before. But now the probability is less than. So what's the area that we are looking for? This area on the left side plus the other area on the right side. So in this case, how can you get this? Another important property of this bell-shaped curve is if you consider all the cases, that means x is from minus infinity to infinity, then what's the probability? You are 100% sure that you will find x in this infinite range. So therefore, the area for this entire bell-shaped curve must be, yes, it's 1 or 100%. But we already know that the area between these two ranges, and this area is what? 68. So 0.68 or 68%. So what's the area left? So in this case, the answer is from the entire area, we want to subtract this blue area. So what's the blue area? 0.68. So we will get the answer 0.32 or 32%. That is the answer. Okay, so it's a kind of reversed case. Previously, we want to know the probability between 62 and 67. In this example, if you exclude that case, what's the probability? Actually, it is obvious. You may subtract from 100% to 68%. So the answer is 32%. Okay, the last question is a little bit more interesting. In this case, we want to know the probability between 59.5. So x is between 59.5 and less than 62. So 62 is the same boundary we have used before, but this is a new boundary. So if you look at this number carefully, as we have done before, it is less than average 64.5, but how much? The multiples of 2.5. So mu and the sigma, right? So how much you will get? Yes, this is a subtraction of 5. So you need, in this case, 2 sigma. So 2 of sigmas you need. Okay, so we have here mu minus 2 sigma. Here, mu minus sigma is a boundary. And what's the area we are looking for between these two numbers? So actually, we are interested in this area. So can we find this area? It's a little bit tricky to find it. However, it's not that difficult. Okay, there could be many different ways to find the solution, but let me use this way. So we are interested in this the red shaded area, right? Because the curve is symmetric, I may consider another same area on the right side. Okay. Then this shaded area, let me draw here. This area plus this shaded area on the right side. How can we get this is, let me use different color for better understanding. So here, I want to draw this blue one. So I will draw this blue shape, bell curve. So this purple area, if I subtract from blue area, I can get these two red areas. So let me subtract this purple area. Does it make sense? Okay, so how can we get this? So actually we already know that. So let's look at this graph. This is what? Between minus 2 sigma, mu minus 2 sigma, mu plus 2 sigma, right? This area is between mu minus sigma and the mu plus sigma area. So we already know that this area is 95%, so 0.95. And we already know this area is 0.68. So from here, if you subtract these two numbers, what you got is 27%. So 0.27 is the answer. So now what we are looking for? We are looking for not two of them, just one of them. So therefore, just one area that we are looking for, let me just use it. Therefore, just one area that we are looking for equals to 0.27 divided by 2. Therefore, it is 0.135 or 13.5%.